Another application of the PERT formula is continuous growth. So anytime something is growing continuously, that PERT formula, we saw it with interest rates and compound interest. If it was compounded continuously, this formula appeared. Well, we can also use this formula for populations. So here we have a population question. It says in Vancouver, 1.38 million in 1981 was the population, and it's been growing continuously. Again, in the old exams, that would be a key that you would have to use your PERT formula. On the new exam, they will give you the formula. And, you know, it might not necessarily say PERT. I've seen this same formula written with an A0 and sometimes with a K. So I don't know if that's an AOEC. It doesn't quite have the same ring. So I like PERT because it's easy to say, but that might show up with different letters. Doesn't matter what letters you have, you can plug things into a formula and use them. So how does this work? Well, find the projected population in 2011 to the nearest tenth of a million. Well, we want to find the population. We know that the initial population was 1.38 million. Our rate of increase, change that to a decimal. And what will I put in for time in 2011? $30, because it's 30 years after 1981. Easy, straightforward question. Why? Well, we don't have to solve for anything. We can just type this into our calculator exactly as we see it. So 1.38 million e to the power 0.017 times 30. Again, and it says to the nearest tenth of the million, so if we round it would be 2.3 million. When will the population reach 6 million? This is where you're going to have to use your logarithms. So because now we're solving for t in the exponent. The answer for the last one was 2.3 million. Yeah. So when will the population reach 6 million? Now we're solving for t in an exponent. Anytime you're solving for an exponent, your brain should go, I have two methods to do this. One is get my bases the same, that's non-calculator. The other one is using logarithms. So that's the first thing that your brain should start going to if you see t in an exponent. Obviously, getting the bases the same is not going to be easy since the base is e. So this will be one that we're going to use logarithms. Now, some of the things that we've done with logarithms, if you take the log of both sides right away, that's not wrong. But then you're going to have to say to yourself, and I'm going to do it and then erase it, but just to point out, if you did this first, okay, you'd have to notice that this 1.38 million is times by this e. This exponent is just to the e. I've been saying this over and over again. We have to make sure that we're using our proper log laws for expanding. If you did it this way, you'd have to add first because of the product law, and then you could bring out your exponent. But what I would suggest instead is I would divide both sides by 1.38 million first. I mean, a bunch of these zeros are going to cancel out. And then you can take the log of both sides. Now, you can take the log of both sides or the natural log of both sides. In this case, in particular, since the base is e, it's going to be nice to take the natural log of both sides. And if you wanted to skip to this next step right away because you can see what's happening, you can see that when you take the natural log of this side, that you can use your log law and bring your exponent out in front, you could go to that step right away. Now the nice thing about using the natural log here is the natural log of e is equal to 1. So when we're dividing to get t by itself, the only thing you would need to divide by is the 0.017, since this equals 1. If you don't remember that it's equal to 1, or in the moment you just forgot that, and you also divided by the natural log of e and put that down there, it's not going to make any difference, because all that means is 0.017 times 1, and that's still going to be 0.017. So whether you have this natural log e there or not, it's going to work out to the same thing. The last thing you're going to do is you're going to go to your calculator. Again, since we're dealing with logarithms and a lot of things in a fraction, it does make sense if you have the fraction button to use it. So on the top of our fraction, we have natural log of 600 divided by 138. And you can even use the fraction button within a fraction if you wanted to, divided by 0.017. And we get 20.99, or approximately 21 years. Yes. Now I was missing a number in my... Oh, I'm missing the 1. Yeah, I am missing 1. If you want to retype something, this is good, also nice. So instead of having to retype the whole thing, if you go second and enter, it'll retype for you what you just typed, which is really helpful to save a little bit of time. And then, now if I insert that 1, that's a better answer, 86.5. Again, anytime you're solving for an exponent, and you have the use of your calculator, check. Did we get it right? Well, I'm going to store this as x, and I'm going to check if I put in 1.38 million times e to the power 0.017 x. That was my original equation. This should equal 6 million if I've done everything correct. And since it does, we know that that answer is right. Okay? So t is 86.5. This is a word problem. We need some, anytime you have a word problem, you need units. So what are we solving for? Is this in centimeters? No, it's when. Well, what did we, this is years. So does this mean in the year 86? Or should we round it and say in the year 87? Well, no, because what is that 86.5 in reference to? That's 86.5 years after 1981. So if we added 86.5 years to 1981, that'll be in 2067. So we could add a sentence here. In year 2067. Halfway through, actually, right? The population will reach 6 million. Another population question. When a population of a herd of gophers was first studied, it was 15,000. 6 years later, it had increased to 18,000. How long is it going to take to triple? So again, this continuously in the past would have told you that this formula is the one that you would use. If this question was on your exam now, they would give you that formula. What are we trying to find? We're trying to find out how long. So we're going to solve for t. But when I look at my question, when I read my question, in order to solve for t, you need to put in a value for a value for p, and a value for r. Can you see in this question you don't know what r is. There's a problem there. Because in order to solve for t, you need to know all the other variables. Now, tripling, we saw how that worked before. You could pick any number and then triple it and put it in for the amount. And no matter what amount you use, whether you use the 15,000 and go to 45,000 or the 18,000 and go to 54,000, it's going to work out to be the same. It's going to take the same amount of time to triple no matter what. But we need that r. So our very first thing that we make a note of is, do we have enough information to find r? If we wanted to find r, we would need to know an amount, a previous, or a starting value, and time. Can you see that we have that? We have a starting amount of 15,000. We're told that 6 years later, it's equal to 18,000. So we can use our formula and say, I have enough information to put everything in and solve for r. Again, at this point, you're solving for r. Where is it? It's in the exponent. How do we solve for something in the exponent? Either base is the same or have to use logarithms. So we're going to use logarithms. Is this one where it would make sense to divide both sides first to simplify it? Yes. So we're going to divide both sides by 15,000. That's just going to get me 18 over 15 equals e to the 6r. Again, since the base is e, and if you want to bring that 6r out in front right away, of course this, this is equal to 1. So we can say that r is going to be the natural log of 18 over 15 divided by 6. So I'm going to go to my calculator. I'm going to write I'm going to use my fraction button. I'm going to have lots of fun with my fraction button this time. I'm going to use I'm going to go natural log. I want to use the fraction button again to write 18 over 15. Notice you have to use your arrow keys to navigate, divided by 6. So that gives me a value for r. Since I've got a value for r, I'm going to actually store this alpha as r. Luckily, I can't tell those letters on my calculator, but the r is above your x. See that little green thing that's fuzzy? That's apparently an r. I mean, you could store it as x, and that's fine, but since I solved for r, why not store it as r? It might be easier to remember what you stored it as later. So now I've got an r value. It was 0.03 ... It kept on going. And I'm going to put those ... dots there to say I'm not going to round my answer early. I'm going to use all of those decimal places right to the end. On any question in grade 12, if you round early and your final answer is off because you rounded early, you lose marks. You lose a half a mark deduction for rounding early. Okay? Sometimes you can round early and get away with it. Like, for example, on this one, I think if you round to like 5 decimal places, you're fine. But maybe 4 decimal places or 3, you might get the final digit off. So your best bet is to store that answer and use all of your values. Now that you have r, we can go to the next step and find t. And again, like I said before, it doesn't matter if you use the 15,000 or the 18,000 or any number. If it's going to triple, watch what happens. So if I use the 15,000, over here would be 45,000 for triple. E, I know that r is 0.03. I'm going to just put ... times t. If I simplify by dividing both sides by 15,000, I'm just going to get 3. Which makes sense because we're tripling. Then to solve our answer, we can take the natural log of both sides. The 0.03 t would come out in front, and you'd get natural log of e. Of course, the natural log of e is equal to 1. So all we would have to divide by is our R value. And when we go to our calculator, we can write our fraction natural log of 3 divided by our R value. Of course, in this case, if you would have just gone second answer on the bottom, that would be fine as well because it's our answer right above. But sometimes you have to do other calculations in between, so it is nice to store that value. And we get 36.15. That's years. What were we trying to find? We were trying to find out how long it's going to take to triple. And of course, you could now store this value as x and check if it works out. Does 15,000 e to the power of r times x equal to 45,000? Yes. Kind of neat because we can store two different values into our calculator. I mean, you got lots of letters. You can store like 26 different values into your calculator. If you ever had calculations that were so complex that you needed to store that much information. If you need to store that much information, you might start using Excel for your calculator rather than using a calculator. One thing we forgot to check if our R value is right. So maybe we want to go back and say, does that work out? And because we've got it stored, we can still do that. 15,000 e to the power of 6r. That should be 18,000. And it is. So we can store our values. Again, storing our values helps us check. It's nice to check things as you're going so that if you'd made a mistake in your R value and then you solved for t and you got t was equal to -5, and you start wondering, wait a minute. So if the population's in 15,000 and it's growing, 5 years ago it was tripled, that doesn't make much sense. And so sometimes you get an answer in the end that doesn't make sense and you're wondering, where did that go wrong? So checking as you go along is helpful. So as you're going along, you can check how you've done, put up different parts of the answer.